Here in Canada, driving in the winter can be dangerous. It's cold, roads are covered in snow and ice. But have you ever wondered why salt being spread on the roads is a solution to that problem? Well, the answer to that question comes from colligative properties. Alright, so colligative properties. What are colligative properties? Colligative properties are really just a property of a solution that depends only on the number of solute particles. So let's remind ourselves of what we're talking about here. We've been talking about molecular substances so far. And here's a phase diagram for a molecular substance. It should look familiar to phase diagrams you've seen already. We've got our gas phase down at low pressure and high temperature. We've got our solid phase at opposite conditions, higher pressure, lower temperature. And we've got our liquid phase in the middle. So this is what a molecular substance phase diagram looks like. But the question is, what happens when we have a mixture? In other words, something dissolved in a molecular substance. So think of salt water, for example, or really, dissolve anything in water, sugar in your coffee. Anything like that is a solution. And the interesting thing about a solution is that the phase diagram changes in a predictable way. And this image is meant to show us that. Put simply, the liquid phase is larger. The liquid phase occupies more range in terms of temperature and more range in terms of pressure. So the line that separates liquid and solid, which is essentially the freezing point at various pressures, shifts. And so the freezing point lowers for a solution. Likewise, the boiling point, which is the line that separates liquid phase from the gas phase, that also shifts out to higher temperatures. And therefore, the boiling point is higher for solutions like that. And likewise, the pressure that, this would be our vapor pressure, right? This line is also indicative of vapor pressure. That also lowers, right? It goes down, which makes sense because vapor pressure going down is almost synonymous with boiling point going up, right? We know that solutions or pure substances with a high vapor pressure are very likely to go into the gas phase. They have low boiling points. So those two are related. And why this happens, or I should say the extent to which this happens, the extent to which the liquid phase occupies more space in a phase diagram, is determined only by the number of particles dissolved in that pure substance. So if I have salt water, really the extent to which my liquid phase of water is expanded depends only on the number of salt particles I dissolve in that system. And it's really purely a statistical effect. And so what I'd like to do today is explain that to you in more detail in the context of all of these different options. Freezing points getting lower, boiling points getting higher, vapor pressures lowering, and there's actually a fourth colligative property. The fourth colligative property is known as osmosis and osmotic pressure. You may have heard of osmosis before. And osmosis is a colligative property. So we'll define what we mean by osmosis and, of course, define what we mean by osmotic pressure in today's lecture. But these are the list. This is all four. These are the colligative properties, which are properties that change only depending on the amount of solute we add in a solvent, right? So if my solvent was water and I dissolved salt into it, the salt would be the solute. And the properties of that solution of salt water are different than the properties of pure water itself in these four very important ways. And these are called colligative properties. So let's take a deep dive into each one of those now. All right, so freezing point depression. We've already seen that the freezing point of a solution is lower than the freezing point of the pure molecular substance, and it's fine for us to use water as an example all day today. So salt water freezes at a colder temperature than pure water. So why might that be? The interesting thing about colligative properties is that they're all effectively statistical, if you will. So let's imagine, in order for me to explain this, I've got a series of water molecules, which I'm going to indicate as blue dots on my screen. And if I want to freeze that substance, so I want to freeze these water molecules, what I need to do is I need to get them to all line up, right? We talked about what the solid state of a molecular substance is, and that is all of the molecules essentially locked in a very regular, very ordered pattern, which for water is governed by the intermolecular interactions between those molecules, which are predominantly hydrogen bonds. So freezing water really means we have to do something like this to it. Bring those molecular particles, if you will, together in a regular ordered pattern. Now, if I have something dissolved in my water, then that means I have, for all intents and purposes, contaminants in this system. So there are other particles that are also in that system, and they have the potential of getting in the way. In other words, preventing my water molecules from being where I would ideally like them to be in the frozen or solid state. This is a purely statistical effect. It's just a result of the fact that there are particles in the way. There isn't necessarily a need for any significant interactions between these particles, but statistically we know that the more contaminant we add, the more likely that those contaminants are going to be in the way of the other molecules that are essentially seeking to freeze, and freezing will be hindered by that. And so the freezing point, you have to get lower. You have to remove even more kinetic energy from this system in order to get all of your water molecules to freeze. They are essentially prevented from freezing by your contaminants. And so this is why the more contaminant you have, the lower the freezing point becomes. It doesn't matter what the chemical nature of that contaminant or solute is. It only matters how much of it you have. So the more salt you add, or the more sugar you add, or the more anything you add to that solution, the lower the freezing point will go. Now we have an equation to help us predict this. This is the equation that allows us to predict this freezing point depression. It's known as delta T with a subscript F. This is the change in the freezing point. So how much lower is the freezing point of this solution compared to the pure substance? That's what delta T is here. And we can predict that new freezing point based on two numbers. One is a constant, ideally called the freezing point depression constant. It's given the symbol uppercase K with a subscript of F. So this is the freezing point depression constant, and all pure substances have one of these. They exist in tables. You can measure them experimentally if you like, but this is a number that quantifies the extent to which your pure substance can have its freezing point changed. Now the next number is M. So this is the molality. Note that word, molality. This is essentially a measure of concentration. In other words, how much of your contaminant is present. The molality will allow you to calculate that because it's defined as the moles of solute you have divided by the kilograms of solvent that you have. Now your solvent is of course your pure substance. So for a given amount of your pure substance, how many moles of solute have you added? So that's why molality is typically another measure of concentration, but it is particularly counting moles. In other words, how many particles are we adding to this pure substance? So moles of contaminant or solute in kilograms of solvent or our pure substance. So M quantifies exactly how much of the particle we've added or the solute we've added. K quantifies exactly how sensitive my pure substance is to colligative properties, and the multiple of those two results in the total freezing point depression. So there are plenty of examples in the notes where we apply this to learn about freezing point depressions for various pure substances. Here is a table taken from the notes where I've listed just a few of these for your information. Water, for example, has a Kf, or freezing point depression constant, of 1.86 Kelvin kilograms per mole. So these units might seem a little bit odd, but they're precisely what we need to work out, according to our equation, what the temperature change will be. More on that in just a second. But this number, again, as I said before, quantifies how sensitive our substances are to colligative properties. Take a look at benzene, for example. Benzene has far less intermolecular interactions than water does. We've talked about water extensively in this class. We know how significant those intermolecular interactions are. And so because of that, water has a characteristically low freezing point depression constant. In other words, it's difficult to mess with water's freezing process. Because this number is so low, we have to add a lot of solute to lower that freezing point. But compared to benzene, for example, its freezing point depression constant is roughly 5 times higher. So it is 5 times more sensitive to solutes. So its freezing point will be more drastically changed as we add a solute to a pure substance, that is benzene. And here is where I can show you that the units for my freezing point depression constant should really be Kelvin kilogram per mole. If the units of molality are mole per kilogram, we'd like to cancel those because ultimately we're trying to predict a temperature change. So if the units for my freezing point depression constant were kelvins times kilograms over moles, the moles in the kilogram will cancel when multiplied by molality. All right, let's talk about vapor pressure lowering and boiling point elevation. We can talk about both of these at the same time because they're intimately related. First, let's think about the statistics, much like we did earlier with the freezing process. Again, I'll pretend I have many water molecules in a sample, and let's imagine those in a surface between where the water molecules stop and the evacuated space above it begins. And so this is our evacuated space above, and this is our surface of the liquid. As you all know, at a given temperature, there is a given likelihood of any one of these molecules jumping into the gas phase simply because it has enough kinetic energy to do so. It may be flying through the solution with enough kinetic energy to eventually go up into the gas phase. And this is representative or represented by the vapor pressure of this particular solution. So and I use the word solution, but in this context, this is actually a pure substance. So this pure substance at any given temperature has a known vapor pressure, which quantifies the amount or the likelihood that any one of these molecules will go into the gas phase. Now, if we can give this system enough temperature and enough kinetic energy so that the vapor pressure matches, and let's use some arrows here to highlight this, so that the vapor pressure matches or exceeds atmospheric pressure pushing down, that's when we say we're boiling. And so that's why vapor pressure and boiling point are so intimately related. If the vapor pressure is high, the boiling point is naturally very low. We don't need a lot of temperature in a substance who has a high vapor pressure. So how are these affected by solutes, contaminants, if you will? Well, let's get rid of our arrows and let's imagine the case where several of these molecules near the surface, some fraction of them, are actually our contaminant. So, if there's some fraction, some percentage of my total system is actually the contaminant, well, what that means is that some fraction of the molecules at the surface are now the other substance, not water. And the vapor pressure here will be affected because not all of the surface is actually my pure substance. So the vapor pressure will be affected purely statistically by how much of this surface is not that pure substance. This is really just a percentage, and it can be quantified with mole fraction. So you will recall mole fraction from our earlier discussions of gas phase properties, but let's imagine the mole fraction of our solvent, right? What percentage, literally by counting the number of particles, which is moles, what percentage of our substance is water and what percent is our contaminant, right? So we need to know, in order to calculate this, obviously, the moles of each. And so the moles of my solvent XSOL will tell me, or at least the mole fraction, by the way, will tell me what percentage or what fraction of this surface is my pure substance and what fraction is the contaminant or solute. And so my vapor pressure will just be scaled down by an appropriate amount. So let's write that down in the form of an equation. My vapor pressure for my solvent in its particular condition here, in a solution, will be equal to the mole fraction, or what percentage of that solution is my solvent, times the vapor pressure of the pure molecular substance, the pure solvent. So I'm indicating that with my superscript of a circle there, which is meant to indicate that this is the vapor pressure of the pure solvent. So when water is pure, and again, it doesn't have to be water, I'm just using that as an example today. When water is pure, this is its vapor pressure at whatever given temperature we're currently working at. If we add a solute, what that effectively does is takes my mole fraction and reduces it from 1 or 100%, which is the mole fraction of a pure substance, and reduces it to less than 1, 80% maybe, or 90%, which would be exemplified by 0.9. So my mole fraction becomes smaller, and therefore my new vapor pressure is just exactly that fraction of my existing one. And it's a simple statistical consequence, meaning that some of my solute particles are simply in the way and not allowing pure substance to evaporate. And so this is really a rather simplistic representation of that, but it works just fine. Now, boiling point is really the same, but boiling point now is specifically referring to when our vapor pressure is equal to the atmospheric pressure. In other words, what temperature do I have to apply to this system, or what kinetic energy do I have to impart upon this system to make the vapor pressure of my solvent equal to or greater than atmospheric pressure? So that's boiling point. And so the boiling point gets higher for exactly the same reason. My vapor pressure is lower. It's less likely that my pure solvent will go into the gas phase because the surface has other particles in the way. And so I have to increase the temperature of this system in order to bring more of those particles up to the surface and evaporate them. Now we can calculate the boiling point elevation using the same strategy as the freezing point depression. In fact, it's an identical equation. The delta T, or change in boiling point, which is shown by our subscript B, is given by another constant, which really looks the same, except I'm putting a subscript of B on it now. So this is my boiling point elevation constant, and all pure substances have a unique boiling point elevation constant, again, times the molality of my solute, right? So how much particles, or how many moles of a solute have I added to a pure substance? And so the more I add, the greater the boiling point will change. But again, this is really a statistical effect. It doesn't matter what the chemical nature of that solute is. It doesn't matter if I add salt or sugar. It's going to affect the properties of the water in the same way. And these are colligative properties. Now there's a fourth and final colligative property I'd like to talk about, which is osmosis. Osmosis, and more specifically osmotic pressure, is a consequence really of having a solution in the first place. In other words, there's no such thing as osmosis in a pure substance. You actually have to make a solution. You have to put a solute in a solvent before osmosis is even defined as a phenomenon. So it's useful to consider this with a picture. Here is a picture giving an example of what osmosis actually is. So osmosis occurs when we have what could be called a concentration gradient, or a difference in concentration between two different solutions that are brought into contact with one another. So take a look at this tube. It's in the shape of a U. Let's call it a U-tube. And if I imagine it filled with water, and I also imagine what's called a semi-permeable membrane there at the bottom. And I also imagine that I've added some solute to both sides of this tube. But clearly I've added more to the right-hand side than I've added to the left-hand side. Now, what is the role of this semi-permeable membrane? Think of it like a filter that allows water to pass back and forth through, but does not allow these solute particles, whatever they are. We can imagine them being salt particles. We can imagine them being some other molecule. But suppose that they're big enough that they don't pass through this semi-permeable membrane. So water's allowed to pass back and forth through this membrane, but these solute particles are not allowed to pass back and forth through this semi-permeable membrane. Now, if I add a different number of these particles to one side as compared to the other side, I have a difference in concentration in these two sides. This is the foundation of where osmosis comes from. Osmosis is the pressure that is naturally present in an effort to equilibrate the concentration on both of these sides. So for example, look at this right-hand side. It is more concentrated. There are more solute particles on this side than there are on this side, which causes a difference in concentration on each of these sides. Naturally, the water will migrate to the right-hand side, because they can, through this semi-permeable membrane, in an effort to equilibrate the concentration on both sides. Notice that if the water level reduces on the left-hand side, it dilutes the particles on the right-hand side while making the particles on the left-hand side more concentrated, right? And this happens in an effort to equilibrate the concentrations on both sides. This is often a stumbling block for students. Students will be puzzled as to why this actually happens. But it can be shown rather simplistically that this is, again, a purely statistical effect. It has only to do with the number of particles on each side. And I suppose in this case, more specifically, the difference in the amount of particles on each side. Now, what happens as the water migrates over to this side is you get a difference now. There is a difference in the water levels in each side of this tube. And so it's essentially a pressure, right? The water in this side will force its way onto this side with a certain amount of pressure to raise the level of water on the right-hand side. That pressure is given the symbol pi. And so pi is what is known as the osmotic pressure. And it's calculated with a relatively simple equation. M is the molarity of the more concentrated side relative to the less concentrated side. So in other words, it's essentially the concentration difference. R is the gas constant, the same gas constant that you know and love working with ideal gases. And T is, of course, the temperature, because this is all temperature dependent. As you increase the temperature, you likewise increase the osmotic pressure. Now, this is a phenomenon that clearly only exists when there is a solution. A pure sample of water on both sides of this tube will cause no effect, and there will be no osmotic pressure, nor will there be any osmosis in the first place. Now, fundamentally, why this happens and why osmosis is a phenomenon in and of itself has to do with a concept called entropy. Now, we don't talk about entropy in Chemistry 1110. We talk about entropy in Chemistry 1112 next semester. But entropy is really just a statistical phenomenon. We talk about what is the most likely arrangement of all of the particles I have in my system. What is the most likely arrangement of where every water molecule should be and where every solute molecule should be? And the way to calculate what the most likely arrangement is the arrangement that has the most options, the most equivalent options. Now, this is a bit of heavy lifting at this point because we've not explicitly talked about entropy, but it can be shown that water molecules being on this side presents the most options for how water is distributed in this system. It is a statistical effect related to entropy, but suffice to say for us that it creates a phenomenon called osmosis, which therefore creates an osmotic pressure. There is a pressure pushing our water over to this side of the tube, and that pressure can be calculated so long as we know the concentration of the particles there. And we also know the gas constant, which is of course always provided, and the temperature allows us to evaluate that as well. Now, there are plenty of examples of osmosis and osmotic pressure calculations in your notes and in the work problems for the week. I would advise to take a look at those and ensure that you understand how they work. Now, the last thing I'd like to talk about today is electrolytes. Electrolytes are compounds that essentially break up in solution. Think of the prototypical example of sodium chloride, for example. Sodium chloride, when dissolved in water, for example, will break up into sodium ions and chloride ions. This is an electrolyte. And why do we care? Why is this important when talking about colligative properties? It's important because, as I said before, colligative properties depend on what? Not the chemical nature of the thing you are dissolving in water, but the literal number of particles, the number of independent objects, be they molecules or atoms, that are dissolved as a solute in that substance. So let me ask you this. If you have 1 mole of sodium chloride that you then place in water, which then quickly dissociates into sodium ions and chloride ions, how many moles of particles did you really add to that water? Well, the answer is 2, because for each NaCl that goes into the pure substance, it breaks up into an Na and a Cl. Therefore, 1 particle very quickly became 2, and 1 mole of these would very quickly become 2 moles of those. Now, that's critically important for colligative properties because that's the only thing that matters. How many particles do you have? So electrolytes are particularly important for us to think about because they completely change the calculations. In other words, if I have an electrolyte that's being dissolved, I need to know how many pieces does that electrolyte generally dissolve into. Now, something like sugar, for example, doesn't matter because it's a carbohydrate. It's not an electrolyte. It doesn't break up. It's not an ionic substance. But ionic substances are electrolytes, and they do tend to break up in solution. And so it's very important for us to recognize that fact and understand that electrolytes need to be accounted for by counting how many particles or ions they really do break up into in solution. Another example might be something like sodium sulfate, which has the formula Na2SO4. Now, sulfate is a polyatomic ion with a charge of -2 generally, and so we need 2 sodium atoms to coordinate with it to form a stable ionic compound solution. So, what does that mean for colligative properties? Well, for colligative properties, it means that this system or this species will break up into 2 sodium ions and a single sulfate anion. And therefore, the electrolyte Na2SO4 is really 3 pieces. So the concentration or the molality, if you will, that we would use for Na2SO4 gets multiplied by 3, and quite rightly so. So when doing calculations with colligative properties, be sure to take this into account when dealing with electrolytes, which is really any substance that will break up when dissolved. And this brings me to another important point. Let's take a look at this table, which is taken directly out of your notes, which shows some data for a couple of different solutions. Let's just take a look at the first one in the top half of this table. Here we're looking at a solution made with sodium chloride, which is precisely the type of system I was just talking about, an ionic substance that will dissociate when dissolved, and every mole of sodium chloride becomes 2 moles in solution. So let's take a look at what would happen here if I add various amounts of sodium chloride to water. So I can get various different molalities, right, which shows you different mass percentages. And so as I go from the top to the bottom of this top half of the table, I get more and more concentrated. And if I measure the change in freezing point for water, for each of these different concentrations, notice that the change in freezing point goes up. So the freezing point lowers to a greater extent for this solution than it does for this solution. Now, if I calculate that freezing point change using the math we described so far today, you'll notice that in none of the cases do I get it right. Now that's because I'm calculating the freezing point depression using the actual molal, right? The concentration of NaCl. I haven't multiplied by 2 in this case. And so what if I calculate the ratio of the measured freezing point change over the calculated freezing point change, I expect to find a value of exactly 2. Now I don't. I find a value of 1.9 in this particular case, but in principle, in theory, I would expect this number to be exactly 2 because NaCl breaks up into 2 particles for every 1 NaCl molecule or 1 NaCl unit. So and 1 NaCl unit becomes an Na and a Cl, and so I would expect the measured freezing point to be about twice as much as the calculated freezing point, unless I took that into account. Taking that into account would be using something called the Van't Hoff factor. Now, the Van't Hoff factor is precisely this. This is the number that would account for that different number of particles, right? So 1 NaCl corresponds to 2 particles in my solution. So that's called the Van't Hoff factor. NaCl would have a Van't Hoff factor of 2. But if I look down this table here, I notice that my number becomes farther off as I go down. In other words, as I get more and more concentrated in sodium chloride, my measured freezing point is farther away from that ideal 2 Van't Hoff factor. So what's actually going on here? What's actually going on here is the difference between ideal and non-ideal solutions. Ideal solutions are the kinds of things I was describing with my cartoon-like image over here, where none of these solute particles interact with the solvent particles to any greater or less than extent than the solvent particles interact with themselves. In other words, these green particles are literally just other things in the way that behave exactly like all of the other particles in the system. That is called an ideal solution. And under those ideal conditions, all of this statistical sort of stuff is exactly right. But what if those particles significantly interact or differently interact with themselves or with other solvent particles? That creates a non-ideal solution. And so what will often happen in reality is sometimes these ions will actually pair up in solution. And this is precisely what's going on in this table. As the solution becomes more and more concentrated in those ionic substances, there's a likelihood that somewhere throughout that solution, a pair of those ions actually do get together and stay together. After all, they are positively charged and negatively charged. There would be a driving force to them sticking together. And if they do, then that means that there isn't exactly twice as many particles in that system as we would have thought. There are approximately twice as many particles, but some of those ions throughout the solution are pairing up. And so that means that as we get more and more concentrated in NaCl, or any ionic species, the Van't Hoff factor deviates more and more significantly from its perfect value. Perfect value being 2 for something like NaCl, and the perfect value being 3 for something like sodium sulfate. And again, we can see that it's not exactly 3, even for dilute solutions. And this is due to ion pairing, which is a result of non-ideal behavior in these solutions. So taking all this into account, we can understand how freezing points and boiling points and osmotic pressure and all of this stuff is dependent on amounts of particles added, and that's colligative properties. And so this brings me back to our icy winter roads, right? So by now you should realize, of course, that salt is really an effective component that has a Van't Hoff factor of 2, and sodium chloride is actually a common road salt. This is what we spread on roads to prevent ice forming, and the reason it works is because it lowers the freezing point of water. So very cold water, water that's below 0, will stay as water and not freeze as ice. But of course it isn't perfect. We know that, of course, If it gets extremely cold, we can still go beyond even the lower freezing point. And so on extreme cold weather, salt is actually ineffective. And this is why salt is usually mixed with gravel and other impurities, so that at the very least you can get some traction over those kinds of things. So that's really how it works. It's a freezing point depression effect, and salt's effective because of its Van 't Hoff factor. Colligative Properties, keeping you safe in the winter.